and welcome to the first of an occasional series of short videos and tutorials based on the human metabolism lectures. This one looks at the range of reaction types discussed in the first of those lectures. A key here is so often is to develop a high level, or if you will, helicopter view of the topic area. This can then be used as a framework to develop your deeper understanding. Now, there are a gigantomous number of biological reactions, and it's all too easy to get lost or even disillusioned by the immensity of it all. I have been known to joke that students don't need to come to lectures. They do, of course. They just need to memorise pathway diagrams like this. That was, as I said, a joke. We build our understanding by appreciating the role of well-defined metabolic pathways, such as these. But before that, we should focus on understanding the relatively small range of reaction types involved. So this was a list that was given in the first lecture. There are many thousands of individual biological reactions, each mediated by their own enzyme. We can make sense of this by appreciating there are 6 main classes of chemical reaction involved. If you can understand and identify them, you're well on your way to making sense of things. As you might have guessed, there are a similar number of enzyme classes that catalyse these reactions. I'm not going to cover them in the lectures or in these tutorials. You do need to know about them, so you should do some background reading. Any good biochemistry textbook will have this information. Okay, oxidation and reduction. Firstly, let's remember for a molecule to be oxidised, another must be reduced, and vice versa, what we call the redox process. We have a couple of definitions for redox processes. The first is based on electrons moving around. This has the useful acronym OILRIG. Oxidation is loss of electrons, reduction is gain of electrons. And there's a nice little diagram summarising the process. Another way of describing redox processes is to decide whether a compound, or often an element within that compound such as carbon, gains or loses hydrogen. Now, this is probably a bit easier to spot than the electron transfer definition. Definition of hydrogen transfer is there. Oxidation is loss of hydrogen, reduction is gain of hydrogen. We can also think of this in terms of loss or gain of oxygen. So pause the video and have a think about how to fill the gaps in the definition for oxygen transfer. Okay, you did pause, didn't you? Oxidation is gain of oxygen. It's quite easy to remember that one. Reduction is loss of oxygen. ATP cleavage, or just hydrolysis, that is taking a molecule and splitting it into 2 smaller fragments. It's an energetic process, hence the inclusion of ATP in the definition. We defined ATP in the first lecture as an activated carrier of phosphate groups. It's often described as the universal currency of free energy. It takes a lot of energy to make ATP from ADP, and that energy is stored in the bonds between the phosphate groups. Okay, here's another pause video moment. What's the sign of delta G for these reactions? And what names do we use to distinguish between reactions with different signs for delta G? Okay, the synthesis of ATP is an endergonic process. That is, it needs energy. And conversely, its hydrolysis to ADP and inorganic phosphate is exergonic, so we can think of it as having released energy. Right, our summarisation. Our summarisation is defined as the arrangement of the carbon skeleton of a molecule. Here's a complicated looking example. These are all isomers of retinol and are intermediates in vitamin A metabolism. We are of course in chemical lazy mode here. I've not explicitly included all carbons or hydrogens except for those in the functional group, which we must include. For fun and profit, you might want to check that they are all in fact C20H30O. You might also want to check that why the top one is called all trans. Have a think about that one. The point about this is they are all isomers of each other. Hopefully you spotted that all the double bonds in trans-retinol are in trans orientation. That is, with the hydrogens on opposite sides of the double bond. You might also want to check why the other 2 isomers are named to indicate that one of their double bonds is in the cis configuration. And to do this, you do need to know how we number the carbon atoms in compounds like retinol. Don't worry too much about this, and certainly don't try to remember this, except to be aware that these conventions are used to precisely define individual molecules. Like I said, it's a bit complicated, and if you need to use this, you just look it up. I'm including it here to help you find the C13 and the C11. If you really want to know more about the nomenclature of retinoids rather, perhaps for an essay, there's a useful guide there quoted on the slide. Okay, group transfer. This is a very common example of group transfer. Actually, when a phosphate group is transferred from ATP to a substrate, and here's an example from glycolysis. Here's the equation including the enzyme. It's worth remembering this is an example of an endigonic process, that is to say the phosphorylation of glucose, being coupled to the hexagonic hydrolysis of ATP. There are loads of hydrolyses around where a molecule is split in two by the addition of water. It's an example of the separation of lactose being hydrolyzed into galactose and glucose by the action of the enzyme beta-lactosidase or lactase. People who don't express this enzyme can't hydrolyze lactose, leading to digestive distress. Okay, addition or removal of functional groups. Here's a reaction we'll talk about a bit later when we review drug metabolism. This is willow bark and willow bark tea. The bark contains acetanilide, which is a mild analgesic. In the liver of bark chewers, the molecule is metabolized to paracetamol, which is easier to excrete in the urine, but a bit more water soluble due to the addition of no H group. Okay, that's the end of part 1. Part 2 will include some examples for you to classify. Thanks for listening.